Okay, guys, I think we got everybody back. I think I'm gonna get started here now. Great job with the group work. I will be trying to do that from time to time throughout the semester, especially now they made this into a 4-unit course. We have a little extra time compared to the last time I taught the class. So that means we have time to practice the material a bit more using group work as a way to do that a little bit. I know not everybody finished the group work. It's totally expected. It's totally fine. The solutions though, just so you're aware, in Canvas, there is a folder called Group Work Solutions. And if you just click into there, you'll find all of the group work solutions and you can review them on your own. If there were problems that you didn't have time to think about very much today, I do encourage you to follow up over the weekend or whenever you get a free moment to try to finish those problems, just so you make sure that you've looked these over and that you feel pretty good about them. Okay. So anyway, I'm going to go ahead and set the group work down for now. And this is the homework that's due tonight. Don't forget there's an assignment. There's only 5 problems on it. One of which, by the way, I think it's the problem number 2 out of the book is literally just proposition 2.9 part 2 in like a contrapositive form. So you have a one-liner for that problem. So one of the, I think it's not the ones I'm going to talk about right now, but one of the problems for tonight is a one-line answer. It's the one about if it's a one-to-one function and something's infinite, the other one's infinite. I forget exactly. Anyway, it's which one? Number 3. It's number 3, the third problem from the assignment. So that one should take you just one breath to write down. There's a couple though that are a little bit more work, and they happen to be put on the board over here. And this is one of them I wanted to go through with you guys a little bit. If we have an infinite set and we pick a specific point from that set and remove it. So if we remove one point from an infinite set, the cardinality does not change. Okay, intuitively the set should be getting smaller, but because the whole thing was infinite to begin with, if you remove one single element from an infinite set, you don't change the cardinality. And then you could imagine that if you then have this set, you could remove one more point and create another set, which would be 2 points less, right? And then 3 points less and 4 points less. So any finite number of points being taken out of an infinite set leaves you with a set that has the same cardinality. Because there's another problem on the assignment that's asking you to prove that the natural numbers are in bijection with the natural numbers take away a certain finite list here. You actually could do this problem by just repeatedly citing this one. You could just say, starting with the natural numbers, let me take out 1. And then from that set, let's just take out 2. And then from that set, let's just take out 3. And before you know it, you'd have this set. And you just have twiddle, 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 twiddle. We know that twiddle is transitive, right? So you could then prove that the natural numbers are in bijection with this set. This is for number 5, I believe. It turns out though, just so you know, it's actually easier for this problem to just make the function, right? So make a function that sends any n to something here. I get too excited about this stuff, and so I start giving away all the answers. So I'm just gonna say that. Okay. It's not too difficult to fill this in. If you're not sure how to actually make this function, shoot me an email later or stop by my Zoom office or in-person office and I'll help you with number 5. Number 5 is not so bad. Okay, it's pretty straightforward. This one, however, is a little tricky. It's like, how do I actually do this? It turns out that the trick to doing this is that you actually have to start by creating an infinite sequence of points within capital X, okay? So what I'm gonna do here, I'm actually gonna sort of give you the solution to this one. So your job is basically to write it up, and that'll make my job of grading it really easy. Which is basically, I'm just going to let x1, comma, x2, comma, x3, comma, dot, 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 going on forever like that, be an infinite sequence of distinct points. An infinite sequence of distinct points. And I can only do that because X was infinite. So if you're wondering where are we using the assumption that capital X is infinite, I'm using it right away in this first sentence. If the set was finite, I wouldn't have been able to do that. This has to be distinct points and it's an infinite sequence, okay? And it has, actually, I'm so sorry. Well, this isn't really a mistake, but I don't want any of these X's to be the little x that was assumed in the beginning. So let's just actually make that little x the first term of the sequence. I should have just done that to begin with. Okay, so guys, I'm gonna make an infinite sequence of points starting with the little x that they gave us, and then additional points that are all distinct from each other, okay? And now I'm gonna define a bijection between the two sets here, right? This is what I have to prove. So I'm going to define f. It's going to go from x to x minus little x via, so, you know, the sets are almost the same. I would love to just use the function send every element to itself. I would love to do that, but I can't quite do that because f of x itself has to be, can't be x, because x is not an allowed output here. So I'm gonna define f of x to be x1. That I can do, because x1 is not the same as little x. And so it does exist in the codomain, right? And then I'm going to define f of x1. Now my problem is the function has to be 1-to-1. So I cannot send f of x1 to x1 because I've already sent f of x to x1. I can't have two different inputs going to the same output, right? So I'm gonna have to shift this f of x1 to some other element. That's where I'm gonna use the x2, right? And then I would love nothing more than for f of x2 to just be x2, but it can't be because again, I would have two different inputs going to the same output, so I have to use x3. And this is why I need this infinite sequence of points, okay? So now, this was kind of scratch work. Let's come over here. I'm gonna define f of y to be the following. If y is equal to x, then this is going to be x1. If y is equal to any of my xn's, then this is going to be x sub n plus 1. And what about all of the points of capital X that are not part of this infinite sequence that we've already been talking about? In that case, we can just define these to be themselves. So, sorry, let's just say f of y equals y otherwise. Does this make sense? This is how you want to define this function. We need it to be a bijection. It has to be a bijection, right? So we write down the function, and then we need to check that f is onto and 1-to-1. I guess I'll start with onto for a moment. Right, we have to start with the onto. And now how does the onto work? I pick something arbitrary over here, right? So how would you like me to write it like this? Let f of y be in the codomain. Would that be a good way? I see people do this a lot. And the trouble with this is that you're already expressing, you're almost, expressing your element as already being f of something when you write this down. So you want to be careful not to write your element as f of something to begin with. What you need to do is pick it to be completely random in here, right? So let's just maybe even use a new letter if it will keep you from getting mixed up with how the function was defined. I would probably just say, let's suppose z is some random thing in the codomain, right? And then my job is to write Z as f of something, right? Now, how am I going to do that? Well, guys, whenever your function is piecewise defined like this, it's defined in cases, your proof's probably going to need cases. You're going to need cases for this, right? So you could say, you know, if Z is equal to x sub I for some I in the natural numbers, so that's a possibility. Z could be one of these elements in my sequence. Then Z would be f of, can we write Z as f of something now? So this is basically saying f of xn is equal to xn plus 1. So I'm shifting down the line on my sequence. So how do I go backwards? How do I go back to the preimage starting from the xi? X sub, which one? Well, I'm going to use xi here. So I want it in terms of I, but there you go. It's just going to be f of xi minus 1. That's exactly right. You know, there's something about this I just don't like very well. I wish that they would have called this first point x naught instead of just x, because you see, I've ended up writing 3 cases up here. You could say, well, wait a minute, if I equals 1, then Z is supposed to be f of x naught, but there is no x naught, right? The first x that I have is x1, so it doesn't really work. If I had just defined this to be x naught, it would be so much clearer. So would you like me to do that? Can we just change the problem? Don't do this on the exam. I'm gonna do it right now. I'm just gonna make this into x naught in the original question, because then my sequence starts with x naught and just flows into the rest of the x's. The beauty of that is, so then down here, this would have been f of x naught equals x1. Then I don't need this case. I don't need that case. I can just get rid of that, and I can just say, okay, so even this works even if n is 0, even for n equals 0. So let's just say for n greater than or equal to 0. So in that case, now I've got something that works really well. Okay, so Z is in the set difference of capital X minus the set of x naught. And now I should be good. Because, by the way, the Z that you have here is not x naught. So now saying that the I is at least 1 is fair, right? You don't have an x naught. So if Z is going to be in this set, it could be x1 or x2 or x3, but it's not x naught, right? You've removed x naught from this codomain, right? So this is great. So we put a check mark there, and then we just say otherwise, Z is just f of Z, and that's also a check mark on that. So f is onto, and that would basically write it up for you there. Okay? Does that make some sense? Okay, perfect. Let me talk about the one-to-one really quickly. For the one-to-one, again, I would try to get away from getting locked into the notation from over here. I would probably, so f is 1-to-1. I would probably do this one. Check that. Check f is 1-to-1. I would probably do this one. Again, we all know the definition, right? You assume that f of one thing equals f of another thing, right? I would probably use some totally different letters again. Maybe f of a equals f of b, right? And then we need to show that a equals b, right? This is the setup of proving a one-to-one function. Okay, but again here, we're going to have to do some cases depending on a and b, right? So the first thing is, so if a and b are both outside of the sequence, the sequence was what? The sequence was x naught, x1, x2, and dot, dot, dot. If they are both outside of that sequence, if they are not any of the sequence terms, well, then according to our function, so this is all I have for my function, guys, just this much right here. In this case, then f of A is A and f of B is B, and so A equals B. And I'm done. In that case, I'm done, you see. Now, is it possible for one of the A or B to be from the sequence and the other one not to be from the sequence? Could that happen? Well, let's see, if A was from the sequence, then it's one of my x's.
Yeah.
And f of that is also one of my x's. But the B, if the B is not from the sequence, then f of B is just B. And that's not from the sequence, whereas this one is from the sequence. It actually can't happen. You can't have one of them be part of the sequence and the other one not part of the sequence. So the only other case, A and B are either both outside of that sequence or they're both inside of the sequence, right? So another possibility then is if, however, A is equal to, let's just say x sub I, and B is equal to x sub j, for some I and j greater than or equal to 0. So that's the other possibility, right? Both A and B are one of the terms of this sequence. Then, since f of A equals f of B, we have, that just means that f of xi would equal f of xj. So, well, what is f of xi? It's xi plus 1, right? So for the sequence terms, you just shift things up. So f of xn is xn plus 1. And so in this case, this would just be xi plus 1 equals xj plus 1. Running out of room, but I'm also almost done. Right? Remember, guys, these were all distinct points. So these subscripts have to be the same now, because you can't have two different x's that are equal to each other. They're all supposed to be distinct. So guys, I plus 1 is equal to j plus 1. Those subscripts have to match in this case. And if those subscripts match, then I equals j. And if I equals j, then A equals B. That's what you needed to prove, right? That's what we needed to show here. So it works in that case as well. So these 2 points, they're either both from the sequence or they're both not from the sequence. And you do have to prove them both. I would not sort of declare that f is 1-to-1 until I'm all the way done with all of this. So I'll say here, thus f is 1-to-1. What I'm trying to say here is sometimes I'll see students who they'll do the first case and then they'll say f is 1-to-1 in this case. And then they'll do another case and they'll say, well, then f is 1-to-1 in this case, right? But fact of matter is that the function is either 1-to-1 or it's not as a whole. It's not sort of in cases 1-to-1. So you actually need to wait until you've shown every case before you conclude that f is 1-to-1, because it's got to be an overall 1-to-1 property. Does that make any sense? Yeah, so that's kind of the idea. Questions on that? Does that make sense? Yeah, and go see. Yeah, the twiddle just means same cardinality. Isn't that weird? You take a point out of a set, it still has the same cardinality if you were working with an infinite set.
Problem, why we need to do 1-to-1? We're just proving that it's the same cardinality.
Well, that is basically the definition of same cardinality, is that there exists a bijection.
Okay.
So going back to that definition, we have to construct a function and then in such a way that we can show that it is one to one. Absolutely. Good so far? Other questions, comments? Yeah, Lindsay,
Quick question.
please.
I just need a clarification as to why when we check for the one-to-one,
Uh-huh.
we split it up into two patients where it's inside or outside.
Yeah, so, the thing is, I'm assuming this much, right? But I don't know where A and B live. The A and the B, those are inputs to the function, so they live in X. But I don't know specifically, are they from the sequence? Because remember what we did here is we made a sequence of points that are in X. And so it makes a difference because of the way your function is defined. You have sort of two parts here.
Nice.
Depending on, so what are the outputs of the function? Well, it depends whether you were inputting something from the sequence, in which case you have to use the top line, or if it was from outside the sequence, in which case you use the bottom line. So you actually have to do your proofing cases as well, and look at all of those. Does that help a little bit? Okay. Awesome. Okay, the other problem that I think was asked for on that sideboard a few minutes ago was the following one. I think it was number 2. And let me just see if I can remember what it said, because I didn't write it down with me here, but I think it says that if A is a finite set, and A star is just some element, is that right? Of B. B is just some big superset, right, that contains A. Then A union A star is finite. Do I have it right?
It says let A and B be sets with A being a subset of B,
Uh-huh.
and then prove that A is finite. Then prove that if A is finite, then A union A star, the set A star is finite.
Okay, yeah, I basically have it right. Okay, so this is basically it. And I really would like you to try on this one also to do as formal as possible with your proof here. So what I mean by that is we gave a definition for finite in the last week sometime. A finite set is one that is either empty, that was one case, or which twiddles some j sub n. Remember the j sub n thing, the set 1 through n? So we kind of need to do both cases, right? So again, this is kind of, because the definition is presented as cases, our proof has to be as cases. So I'll just say it this way, since A is finite, A equals the empty set, or A twiddles j sub n for some natural number n. A has a bijection with some j sub n. So those are the two cases. And so we kind of have to do them as two cases. So case 1 would be if A is empty. Right? Case 1, so we have either this is one possibility or this is the other possibility. Those two boxes. We have to kind of look at both of these. Now, if A is empty, then when I take the union of A with this extra point that is just being denoted as A star, then that would just be the empty set union the set of A star. And what would that be? It's just the set of A star, right? If you take the empty set and you union that with anything, it just gives you the other thing back again, right? So now the question is this finite? It is very finite, but technically to convince me of that, we would have to use the definition. So I would have to know, is this empty or does it twiddle J something? What would you say is the right answer to that? It twiddles J. And 1. J1. It twiddles J1 because there's only one element here, right? It twiddles J1. What's the bijection? The bijection just sends f of A star to the number 1, right? And that's pretty trivial, basically, that's a bijection. So technically, in that case, you're twiddling J1, and so thus a union, the set of A star, is finite because it twiddles some J sub n. That's case 1. Okay, then we've got to do case 2, Case two is that we're assuming that A already twiddles Jason N for some N in the natural numbers. Now, the interesting thing is, when we look at A union A star, the A star lives in B, which is the big set that contains A. But that A star could actually be inside of A itself. Or it might not. Right, we don't know. So here's A and then here's B, right? I like to draw these pictures. If it's possible that the A star is inside of here. So let's just dispense with that first, guys. If A star is in capital A, if it's already in capital A, then I think you guys know that if we take A union A star, we would just still get just A, right? If you're taking the union of something that's already in A, then throwing it into the union of something that it's inside it doesn't make it any bigger. And A is already finite, so which is already finite. So this is already good, which is already assumed finite, right? The original problem assumed that A was finite. So we would be done in that case. The more interesting case would be, and by the way, this is kind of sub cases of case two, right? This would be, what if the A star is not inside of A? That's the more interesting case, right? Then how would you convince me in this case? So then we're going to look at A union A star, and I want to know that I want to prove that that's finite. Now to prove that it's finite, I have to prove that it's either empty, this isn't empty, or that it twiddles J something. And I'm wondering, do I have any proposals out there? Is this going to twiddle something? Keep in mind, I'm in case two, so I already know that A twiddles J sub N. So what do you think that this new set, A union A star, would probably be twiddling? J sub N plus one, right? There's one more element now in that set. So if we assume that A basically has a cardinality of N, and now you're throwing in another element that was outside of A, well, then you're going to make that set larger. One more element in it, which would be this. Okay? How do you guys feel about that? Yeah, it's a similar case by case analysis that you have to do there. You guys are all good with that? I am okay with that. I would like to point out that if we really wanted to get super squirrely about this, right? What we might want to do is we might want to say, okay, so we have a bijection already here, right? So this is given. And then, if you're trying to claim to me that there's a twiddle here, then that means you're creating a bijection. So, right, to prove that one thing twiddles another, there has to be a bijection. So you now would have to define G. So you don't need to do this. I'm not gonna totally ask for it, but when you read my solutions, you might see that I actually do go into all of this. So what I would do then is I would define a new function, which would take me from this set to this set via, see what I'm saying? Now I'm gonna actually make a bijection here. If I'm putting a twiddle here, then I'm saying there's a bijection there. And so technically I should write it down. And how would this bijection work? Well, I would input something, call it little x, and I would say, look, if x is not equal to A star, right? So the inputs are coming from here. If the x is actually from the original set A, then I can just use whatever f was for that. Whatever the f of x was, because f was a bijection that took all the elements from A and gave me something between 1 and n, right? But then if the x was equal to A star, what output do you suppose I would write down here? One more time? Actually, the input here is A star. So the x is going in right here as the input to the G. What would be the output? keep in mind where your outputs are living. I need a number between 1 and n plus 1. All of the numbers from 1 to n are gonna get used up by the outputs of f. So this has to just be that very next number, right, in that set J sub n plus 1. So this would be how you would actually write it down. Oh my gosh, then you'd have to stop and prove that it's 1-to-1 and onto, and again, because it's defined in cases, you would have cases, just like we did in the earlier problem, that you'd have to show here as well, okay? I'll let that slide. If you just want to kind of write this much, I'm happy to accept that it's pretty clear that this union here is going to twiddle J sub n plus 1. But if you wanted to be super careful, dotting all of your i's and crossing all of your t's, this would allow you to do it. Okay, so I would just say now must check G is a bijection. Technically, that would have to be done, but I will let you leave that out if you don't want to write all of that up. If it's helpful for you to do it, by all means, go ahead. You can try and do it. I've got solutions online for you to consult with that as well. But I'm feeling guilty enough as it is, just giving you 5 days to turn this homework around, 4 days really, to do this homework. So I think I did the 2 hardest problems. Here, of the other 3, one of them is trivial and the other 2 are pretty quick. You don't have to write a whole lot down. So I think I'll leave it at that. If you do have more questions on the homework though, I hope you'll stop by or stop by just to introduce yourself as well. That would also be great. Wow, I'm always amazed how fast the time goes by. We've gone through almost 2 hours already. Is everybody hanging in there? Okay, so I don't have a lot of time to do a whole lot else today. That's okay. We are gonna take 10 minutes to start, or 8 minutes to start, kind of get you previewed into what I'm gonna do next, which is we're gonna go back to section 2.1 of the book. And this is all about the structure of the real numbers. And I'm pretty certain that most of this is going to be very familiar to you guys, but I just want to be very thorough about this. How many of you have taken Math 302, the sort of modern algebra class? Okay, a couple of you have. In an abstract algebra class, they'll teach you, for example, what groups, rings, and fields are. And the real numbers are a field. That's an algebraic structure, and it's equipped with addition, subtraction, multiplication, and division, right, with a bunch of properties. So the book starts by reviewing all of those algebraic properties, but this is not really an algebra class. So I'm not going to dwell on those properties. There's a bunch of axioms. So we have many axioms to develop the real number set. Okay, and the book sort of starts off this chapter. I'm back now at the beginning of chapter 2. It starts off this chapter by kind of giving you a quick reminder about some of these axioms. So 2.1 through 2.5, these axioms, there's like 5 axioms here, and these all deal with, these are familiar properties of addition, subtraction, multiplication, and division. So I'm just going to write these very sort of abbreviated notations here. By the way, if anybody still doesn't have the book, I do have physical copies. And if you needed to stop by my office, I think I sent out a scan of at least the beginning of chapter 1. But if anybody's missing any of the book, you can come by my office anytime and borrow my book. That's totally fine. But anyway, the book starts off by reminding you that addition is commutative. Addition is associative. There's a distributive property, like all this basic algebra that you've done with numbers your whole life, right? So it's just kind of 5 axioms worth of review there. But what I want to focus on really are the so-called order axioms, how we sort of put these real numbers into an ordering. So we're going to add this as well. So there is a notion. So there, in addition to the algebra, the familiar properties of algebra, so maybe I should just make that really clear here, guys. I'm talking about familiar algebra properties, those first 5 axioms, 2.1 through 2.5. There is also a notion of order that we can talk about, putting numbers in order, and we use a less than symbol for this, which of course you can turn around and draw it as a greater than, and that's also fine. But a notion of bigger versus smaller. One number is bigger than another or smaller than another. And so there are some additional axioms. And I'm gonna actually write these out in full. Remember, guys, when I'm talking about an axiom, it's not something we have to prove. An axiom is sort of just an assumption that you're gonna make. You're just saying, I'm going to assume that I can do something, right? And that's one of the things that drew me to math. I was like, oh, I get to make up my definitions and play with them. Yeah, that's kind of how this works. So that's what we're gonna write down right now. So the first axiom, 2.6 here, is that for all real numbers A and B, right, exactly one of these holds. Exactly one, and I'm gonna write down 3 possibilities. One possibility is that A is equal to B. The second possibility is A could be less than B. And the third possibility would be that A is greater than B, but I'm gonna write it using the less than again, just to keep using the less than, but you could, there's nothing wrong with using a greater than. But this is called the, I'll just put this over here, this is called the trichotomy property. Trichotomy, tri means 3, there's 3 possibilities. If you take any 2 numbers, exactly one of those 3 things is true, no more and no less. Okay, so that's the first axiom, it's pretty clear. So with that done, let me just jot down the next couple of axioms. I've only got 3 minutes to do this, so this is not going to take long. So axiom 2.7 just says if you take 3 numbers, 3 real numbers, A, B, and C, if A is less than B, then A plus C is less than B plus C. So inequalities will respect adding the same thing on both sides. Of course, C could be a negative number, which would effectively be subtracting from both sides. So this is nothing surprising. And here we see the order axioms interacting with the algebra axioms, because I've got plus signs that I'm referring to here. Next one, 2.8. Can everybody read this if I put this here? Legible, hopefully. Okay, 2.8. So what does this say? This is also for all A, B, and C in the real numbers. And again, if A is less than B, and we take C to be greater than 0. Now, I'm using a greater than here, but again, I really could write it the other way, 0 less than C. I'm just saying that C is a positive number. Then A times C is less than B times C. So again, guys, this is an axiom. I'm actually assuming if somebody ever walking down the street, somebody asks you why this is true. I don't usually get asked questions like that down the street, but you never know. Somebody asks you why that's true, you just say, we're assuming that that's true. That is an axiom that we are going to just take for granted that that is actually true. So there's something that I'm sure is very familiar to you. If you multiply both sides of an inequality by a positive number, it doesn't change that inequality at all. Right, so we'll go ahead and take that for granted as well. Let me write down one more here, 2.9. So there's already 9 axioms. Again, I didn't write down the first 5, the algebra axioms. You can look those up in the book if you'd like to. But let me just write this one down. Axiom 2.9 for all A, B, and C in the real numbers again. So starting off the same way. If A is less than B and B is less than C, then A is less than C. It's some kind of a transitive property of inequality. There's nothing too surprising about that. In the homework that you're gonna be doing for next week, so I guess that'd be number 4. You can use all of these axioms to prove the amazing fact that 0 is less than 1. Okay, so use these axioms. You'll see it, this is in the book, so you don't need to write this down. To prove that 0 is less than 1. And then from there, you can prove that 1 is less than 2 and 2 is less than 3. So you can get all of the integers ordered, right? Smaller versus larger, and you can take any 2 integers and compare them in such a way. And you can prove that, for example, 1/2 is between these 2, right? Because if 1 is greater than 0, then you'll be able to prove that 1/2 is greater than 0 and stuff like that. It's kind of interesting how these things work out. And the book will challenge you to do all of that. So on Thursday, we're going to talk about absolute value a little bit. I'm sure you all have been exposed to it, but we'll try to prove a few properties. Triangle inequality is a good one. And a couple other inequalities that come up a lot in analysis. And then we're going to really start to get into things like upper bounds and lower bounds of sets. We can't talk about that if there's no ordering in place. So we'll have to have an order, a notion of bigger versus smaller, and we can use that to talk about things like supremums and infimums, which is one of the hallmark topics in Math 350. So we should be able to work our way into that a little bit next time. So guys, thanks for being here in person today. It's great to see all of you. Quick reminder, if you haven't had a chance to stop by and say hello to me, I am going to drop your lowest homework if you stop by and just introduce yourself for a couple minutes. Feel free to do that. I'm going to try to go next door, but if that doesn't work, because I don't know who's in there, I'll be down in my office, down in the basement of the building. I'd love to talk to all of you. Have a great rest of your Tuesday, and we'll see you next time.
Does it count if I was the first person to see this morning?
Yes, you are good. You are already good.